Hello, I am Sunita. Welcome to my class. Here I am going to discuss JPSTR science topics according to the syllabus. Here the topic is magnetism. In this one we will study in detail about diamagnetic, paramagnetic and ferromagnetic materials. Let us discuss here magnetic materials. Materials that can be magnetized in the presence of a magnetic field. If you placed a material in the magnetic field, then it will get magnetized. That material we will call it as a magnetic materials. Generally, we are having three types of magnetic materials. One is the diamagnetic material, second one is paramagnetic material, third one is ferromagnetic materials. Let us discuss in detail three types of materials. If you keep, otherwise if you placed a different types of materials near to the magnet, what are the changes? Let us observe here. First one, diamagnetic materials. If you placed a diamagnetic material near to the magnet, then that diamagnetic material, it will be weakly repelled by a magnet. Then second case, if you keep paramagnetic material near to the magnet, then it will be weakly attracted by a magnet. Then third one, if you placed a ferromagnetic materials near to the magnet, then it will be strongly attracted by a magnet. Then here we will discuss if you placed a magnetic material in a magnetic field, then how that materials, how they will be magnetized. Let us discuss here. First one, if you placed a diamagnetic materials in a magnetic field, then that material, it will be weakly magnetized in the opposite direction of the magnetic field. This diamagnetic material, it will be weakly magnetized, but it will be in opposite direction of the magnetic field. See the arrow mark here, it should be opposite to the magnetic field. Because of this opposite side, its value is negative. It will be weakly magnetized, therefore the magnetized value, it will be very small. The next one, in the case of a paramagnetic material, if you placed a paramagnetic materials in the magnetic field, then it will be weakly magnetized in the same direction of a magnetic field. It will get weakly magnetized, but in the same direction of the magnetic field. See the arrow mark, it will be in the same direction of the magnetic field. The value is positive because direction of magnetic field, direction of the paramagnetic materials, both are same. Then therefore it will be positive, but it will get weakly magnetized, therefore its value is very small. In the case of a ferromagnetic materials, if you placed a ferromagnetic materials in the magnetic field, then it will be strongly magnetized in the same direction of a magnetic field. This also, it will be get strongly magnetized in the same direction of a magnetic field. Therefore, same direction, its value is positive. It will be strongly magnetized, therefore its value is very large. If you placed a diamagnetic, paramagnetic, ferromagnetic materials in a magnetic field, then how magnetic field lines, how they will behave with these different materials, let us discuss here. First one, in the case of a diamagnetic materials, if you placed a diamagnetic material in the magnetic field, then magnetic field lines, they will be, you can see the repulsion from the center of the materials. Repulsion of magnetic field lines of force from the center of the materials. The magnetic field lines, they will get repelled from the center of the material in the case of a diamagnetic materials. In the case of the paramagnetic materials, if you placed a paramagnetic materials in the magnetic field, then magnetic field lines, they will be attracted from the center of the materials. Attraction of magnetic field lines of force towards the center of the material, then magnetic field lines, they will get attracted from the towards the center of the materials. They will get attracted towards the center of the material in the case of a paramagnetic materials. Then in case of ferromagnetic materials, if you placed in the magnetic field, then you can see the heavy attraction of magnetic field lines of force towards the center of the materials. Then this magnetic field lines, they will be attracted towards the center of the materials. If you placed a diamagnetic material in the non-uniform magnetic field, then that material it will move from strong field region to weak field region. Then in the case of a paramagnetic material, if you place that one in non-uniform magnetic field, then that material it will move from weak field region to strong field region. In the case of a ferromagnetic material, if you placed in a non-uniform magnetic field, then that material it will be moved from weak field region to strong field region. Let us discuss here. If you remove an external magnetic field, which are the changes it will happen here? Listen here. In the case of a diamagnetic material, they lose their magnetism on removal of external magnetic field. If you remove an external magnetic field, immediately it will lose their magnetism, and also it does not have any unpaired electrons. All the electrons they will be paired up in the case of a diamagnetic material. Let us discuss in paramagnetic material. They lose their magnetism on removal of external magnetic field. Here also on the removal of external magnetic field, here also it will lose its magnetism, but it contains an unpaired electrons. In the case of an ferromagnetic material, they do not lose their magnetism on removal of external magnetic field. Here in the case of a ferromagnetic material, if you remove an external magnetic field also, it will not lose their magnetism. It will behave as a permanent magnet and it contains an unpaired electrons. Diamagnetic materials, it will be in solid, liquid, gaseous state. It can exist in all the three status also. For example, water, copper, mercury, gold, hydrogen. Water is the example for liquid state, copper, mercury, example for solid state, hydrogen, example for gaseous state. Then paramagnetic material, this one also it will exist in solid, liquid, gases. Aluminium, platinum, sodium, crown glass. These are the example of a paramagnetic materials. Then ferromagnetic materials, they will exist only in solid state. Only in solid state, remember that one. For example, iron, nickel and cobalt. Let us discuss in detail magnetic and non-magnetic behavior of a substance. You know that all matter is made up of an atom. Each and every matter is made up of an atom. Then each atom it contains a positively charged nucleus. It is located at the center of the atom. Then this electrons it will be revolve around the nucleus. When electrons revolve around the nucleus of an atom, then it will constitute a current loop. You know that electrons it will be revolve around the nucleus, then it will generate a current loop. Then the direction of the current loop it will be opposite to the direction of the motion of an electron. This current loop it will behave as a magnetic dipole. Then the generation of current loop it will behave as a magnetic dipole or atomic dipole and has a magnetic moment M, it will be equal to I into A. Then this magnetic dipole it is indicated by this arrow mark. Then this arrow mark it will indicate north south direction of an atom. Here you have to remember the matter is made up of an atom. When electrons revolve around the nucleus of an atom, it will constitute a current loop. Because of this current loop, an atom it will possess a magnetic dipole. Then this current loop it will be in the opposite to the direction of the motion of the electron. This it will constitute a magnetic dipole or atomic dipole. It is indicated by this arrow mark. Let us discuss the cause of diamagnetism, paramagnetism and ferromagnetism. In certain materials, all electrons are paired. The magnetic moment of paired electron cancel each other and the net magnetic moment is 0. In certain materials, like in the case of a diamagnetic materials, electrons they will be exist in a paired electrons. Paired electron means two electrons. Here consider this is one electron, this is the second electron. In the first electron, consider this is the direction of the motion of the electrons. Then current loop it will be generated in the opposite to the direction of motion of an electron. Therefore, in the first case, this is the direction of an current loop. Then magnetic moment generated by first electron is indicated by up arrow mark. Then in the case of a second electron, consider this is the direction of an motion of an electron. Then current loop, it will be generated in opposite direction, in this direction. Then magnetic moment generated here, it is indicated by down arrow mark. In the case of a paired electron, one electron, it will generate a magnetic moment, it is indicated by up arrow mark. Then another magnetic moment, it is generated by another electron, it is indicated by down arrow mark. Then here you can observe magnetic moment generated by two electrons, they will be in opposite direction. Therefore, the magnetic moment of paired electron, it will be cancel each other. Therefore, net magnetic moment is 0. In the case of a diamagnetic material, net magnetic moment is 0. Then in the case of a diamagnetic material, there is no atomic dipole, there is no separation of charges, you can see in the case of a diamagnetic material. Second point, in another, electrons are unpaired, net magnetic moment is not 0. Unpaired electrons means electron, it will be exist in only one. Then here consider, here in this case, this is the direction of an electron. Then current loop, it will be generated in opposite direction. Then magnetic moment, it is indicated by up arrow mark. Here it will exist only one magnetic moment, only in one direction. Therefore, this one you can observe in paramagnetic and ferromagnetic material because they contain unpaired electrons. Therefore, magnetic moment in the case of a paramagnetic and ferromagnetic material is not 0. Then you can observe paramagnetic and ferromagnetic, you can observe a atomic dipole. Consider a sample of magnetic material which contains thousands of atoms. For example, paramagnetic and ferromagnetic materials. In the case of paramagnetic and ferromagnetic materials, they contains thousands of atoms. Thousands of atoms is nothing but thousands of magnetic dipole. But here in the case of an external magnetic field, this magnetic dipole, they will be randomly oriented. Therefore, net magnetic moment, it will be 0. Here you have to remember, in the case of an external magnetic field, the magnetic dipole, they will be randomly oriented. Because of random orientation, net magnetic moment, it will be 0. This can observe in the case of an paramagnetic and ferromagnetic material. When this sample means in the case of a paramagnetic and ferromagnetic material is kept in an external magnetic field, then TARQ act on an atomic dipole or magnetic dipole and tries to align dipole in the direction of an applied field. Already I explained, in the case of a paramagnetic and ferromagnetic material, in the absence of external magnetic field, the magnetic dipole, they will be randomly oriented. But when you apply a magnetic field, the TARQ acts on an atomic dipole. Therefore, all the magnetic dipoles, they will be aligned in the same direction, aligned in single direction with the help of an applied field. In this case, net magnetic moment, it will be not 0. When the atomic dipoles, when they are randomly arranged, net magnetic field, it will be 0 because they will be cancel each other. Because of that, net magnetic moment, it will be 0. If the atomic dipoles or magnetic dipoles in the presence of an magnetic field, they will be aligned in single direction, in one direction. In this case, net magnetic moment, it will be not 0. Then they will possess some amount of magnetic moment. Let us discuss what is mean by magnetization. If you keep some materials in an external magnetic field, you know that material, it will get magnetized. Every material, it has atomic dipoles. When you keep that materials in an external magnetic field, that atomic dipole, they will be aligned in a proper pattern. When they aligned in a proper pattern, in that case they will get magnetized, otherwise they will get magnetization. Then magnetization, it is indicated by I, magnetic moment per unit volume. Definition of magnetization is nothing but the magnetic moment, otherwise magnetic dipole, how much they will get aligned per unit volume. Therefore, it is given by the formula I, it will be equal to m into V, magnetic moment per unit volume, how much magnetic dipoles they will get aligned per unit volume, it is given by magnetization. Then magnetic moment, it is given by the formula I into A, then V divided by V, then SI unit of I, it will be ampere, then SI unit of area is meter square, then SI unit for volume is meter cube. Meter it will get cancel. Then the SI unit of magnetization, it will be equal to ampere per meter. Let us discuss in detail magnetic intensity or magnetizing field H. Consider a solenoid carrying a current I and a soft iron bar core is placed in it. Consider this is a solenoid. Solenoid is nothing but a current carrying conductor you have to wound with the help of a copper wire. When you switch on the current, then the current, it will flow in this direction, then it will produce a magnetizing field H. Then one more thing, you have to keep a iron core inside a solenoid. Then here iron, it will behave as a ferromagnetic material. Then magnetic field inside the solenoid is due to two factors. One is external factor, another one is internal factor. External factor means, already I explained, when current flow inside the solenoid, because of the flow of the current, it will produce a magnetizing field H. Internal factor, how it will get magnetized means, iron, already I told, it will behave as a ferromagnetic material. Because of this magnetizing field, because of this magnetic field H, inside the iron core you are having magnetic dipoles. Because of this external magnetic field, this magnetic dipole, they will get aligned in the proper direction. Then this iron core, it will get magnetized. Because of this magnetization, then it will produce a magnetic field. In this way you can observe, inside a solenoid it will produce a, otherwise it will create a magnetic field. Net magnetic field inside a iron core, it is given by, it is indicated by B. B is directly proportional to magnetizing field H, this is the external factor, plus I, magnetization, this is the internal factor. Let us listen here, let us see here. This is the solenoid. If you applied a current, then the current, it will move inside the solenoid. Because of the flow of the current, it will produce the external magnetizing field H. This H, it is indicated by external magnetic field H, because of the flow of current inside the solenoid. Then this I, it is nothing but magnetization. If you keep a iron core inside a solenoid, because of the external magnetic field inside the iron core, magnetic dipole, they will align in a proper direction because of the external magnetic field. Because of the alignment of magnetic dipole, then that iron core, it will get magnetization. Because of this magnetization, it will add external magnetic field. Therefore, net magnetic field B is directly proportional to magnetizing field H plus ionization I. If you remove this proportionality constant, in place of this one, mu naught will come. Then B, it will be equal to mu naught into H plus I. Here B is net magnetic field. Mu naught is the proportionality constant. H is the external factor magnetizing field. I is the internal factor magnetization. This one you have to remember. Then unit of external magnetic field or magnetizing field H is given. It will be equal to unit of magnetization. It is nothing but ampere per meter. This one also you have to remember. Magnetic susceptibility zeta. First one, the magnetization of a material is influenced by external factors. Second point, stronger the magnetizing field H, more is the magnetization. If you apply a strong magnetic field, then inside the iron core you are having a magnetic dipoles. If you applied a strong magnetic field, then that magnetic dipoles, they will get aligned in the proper direction. Then alignment it will be more if you applied a powerful, otherwise stronger magnetic field. Therefore I it will be directly proportional to H. If you remove this proportionality constant, you have to use this constant. This one we will call it as a zeta. Then I it will be equal to zeta into H. SI unit of I is ampere per meter. Then SI unit of H is same, ampere per meter. These two SI units, they will get cancelled. Therefore the SI unit of magnetic susceptibility is zeta. It will be dimensionless, otherwise it don't have any units. Let us see few formulas. Absolute permeability mu naught, magnetic permeability mu, and relative permeability mu r. Net magnetic field in any material, you know the formula. B it will be equal to mu naught into H plus I. Consider in the case of a vacuum. In vacuum you are not having any atoms. There is no magnetic dipole. There is no alignment of magnetic dipole takes place. Therefore magnetization it will be 0 in the case of a vacuum. Therefore I it will be 0. Substitute in this formula. Then B naught it will be equal to mu naught into H in the case of a vacuum or no medium. Then consider the second case. For any other material, Bm it will be equal to mu naught into H plus I. You know the formula. I it will be equal to zeta into H. Substitute the value of I in this formula. Bm it will be equal to mu naught into H plus, in the place of I, zeta into H. In this formula H is a common. Therefore Bm it will be equal to mu naught 1 by zeta into H. Then here mu naught 1 by zeta, in place of this one we can write mu m, because this is for a particular material. Then Bm it will be equal to mu m into H. Next one. Third formula, mu r it will be equal to mu m divided by mu naught. You know the value of mu m, it will be equal to mu naught 1 plus zeta divided by mu naught. Mu naught it will get cancelled. Mu r it will be equal to 1 plus zeta. Then next formula, mu r it will be equal to mu m divided by mu naught. This is the another form. You know the value of mu m. Mu m it will be equal to Bm divided by H. Then mu naught it will be equal to Bm divided by H. H get cancelled. Then you will get Bm divided by B naught. These are the few formulas up to we have studied. Let us recall the formulas. Let us recap the formulas what we learned up to here. Let us discuss in detail diamagnetism. In an atom of some materials, electrons are in pairs. In the case of a diamagnetic materials, electrons they will be exist in pairs. The magnetic moment of paired electrons cancel each other. Net magnetic moment of an atom is 0. In the case of a diamagnetic material, the magnetic moment of one electron is showing upward. The magnetic moment of another electron is showing downward. Then these two magnetic moment they will be opposite each other. Therefore they will cancel each other. Net magnetic moment of an atom is 0. Then in the case of a diamagnetic material, no atomic dipoles. Example of a diamagnetic materials are copper, water, air, hydrogen, etc. When an external magnetic field is applied across any material, there are two effects. First one, if there are atomic dipoles in material, they align with external field. That one we will call it as a magnetization. If the material, if it is having atomic dipoles, then with the help of an external magnetic field, that atomic dipole they will get aligned in the proper direction. Then that material it will get magnetized. That process we will call it as a magnetization. This effect you can observe in paramagnetic ferromagnetic material. This is not possible in the case of a diamagnetic material, because diamagnetic material it does not contain a atomic dipoles. Second point, there is an induced magnetic dipole moment in each atom of a material. The magnetic field due to these induced dipoles always oppose the applied field. This one we will call it as a Lenz's law. By the application of an external magnetic field, each atom of the material it will get induced magnetic dipole. Because of this induced magnetic dipole, it will generate a magnetic field. But this field is always oppose the applied field. This one we will call it as a Lenz's law. This property you can observe in diamagnetic, paramagnetic and even ferromagnetic material also. Let us discuss here when you applied an external magnetic field, which are the effect you can observe in the case of a diamagnetic substance. First one, there are no atomic dipoles, so no alignment occurs. In the case of a diamagnetic substance, no atomic dipoles, therefore no alignment occurs. Second one, the induced dipole moment occurs which weakly opposes the applied field. Look at here. When you applied an external magnetic field, then these atoms they will acquire an induced dipole moment. Because of this induced dipole moment, they will generate, otherwise they will exist a magnetic field. Then this magnetic field it will oppose the applied field. Because of this reason, diamagnetic substances are weakly repelled by an applied magnetic field. This point you have to remember. This one they may ask in the exam. Let us discuss the property of diamagnetic substances. First property, the magnetization is slightly negative due to induced magnetic moment. Already I explained, when you applied an external magnetic field, the atoms they will acquire an induced magnetic moment. Because of this induced magnetic moment, the atom it will get magnetized, otherwise the material it will get magnetized, and this induced magnetic moment it will opposes the external magnetic field. Because of this reason, magnetization I it will be slightly negative. Next point, magnetic susceptibility zeta is small negative. Zeta it will be less than 0. For example, zeta value it will be minus 10 to the power of minus 5 for copper, because magnetization I is directly depends upon the magnetic field, and also if magnetization is negative, zeta also it will be negative, because both they will be directly proportional to each other. Third point, when a diamagnetic substance is kept in an external magnetic field, the magnetic field inside a diamagnetic is slightly less than the external magnetic field. If you keep an diamagnetic substance in an external magnetic field, because of this induced dipole moment, this it will opposes the external magnetic field. Because of this reason, the magnetic field inside a diamagnetic substance is slightly less than the external magnetic field. The net magnetic field it will be given by, it will be equal to mu naught H plus I. Next property, when a diamagnetic substance is placed inside a magnetic field, the magnetic field lines become slightly less dense in the diamagnetic substance. In the case of a diamagnetic material, the magnetic field inside the diamagnetic material, it will be slightly less compared to the external magnetic field. Because of this weak magnetic field, the magnetic field lines inside a diamagnetic material, it will be slightly less or slightly dense. Fifth property, in a non-uniform magnetic field, a diamagnetic material tend to move from stronger part to the weaker part of the magnetic field. In non-uniform magnetic field, already you know, inside a diamagnetic material, there will be an induced magnetic dipole. Because of this induced magnetic dipole, it will create a magnetic field. This magnetic field, it will oppose the external magnetic field. Therefore, if you keep a diamagnetic substance in non-uniform magnetic field, then this material, it will move from stronger part to the weaker part of the magnetic field because of this induced magnetic dipole. Next property, sixth one, the behavior of diamagnetic material is independent of temperature. Susceptibility does not change with temperature. Look at the graph here. The graph between susceptibility and temperature, you will get a flat line. This, it will indicate the behavior of diamagnetic substance does not depends upon the temperature. Seventh property, relative permeability mu r is slightly less than 1. You know the formula, relative permeability mu r, it will be equal to 1 plus zeta. Already you know zeta value is slight negative, 1 minus negative, then you will get a value less than 1. Therefore, relative permeability mu r, it will be slightly less than 1. Let us discuss in the case of a paramagnetism. First point, in some materials, electrons are unpaired and net magnetic moment of an atom is not zero. In the case of a paramagnetic material, you can observe a unpaired electron. Because of the presence of an unpaired electron, it will possess some magnetic moment. Therefore, in the case of a paramagnetic material, the magnetic moment, it will be not zero. Second point, so there are atomic dipole in paramagnetic substance. Yes, atomic dipole, it will exist in paramagnetic substance. Example, chromium, manganese, copper sulfate, O2 at standard temperature pressure. Next point, in the case of a paramagnetic material, in the absence of an external magnetic field, the atomic dipoles are randomly aligned and net magnetic moment of material is zero. In the absence of an external magnetic field, if H is zero, then atomic dipoles in paramagnetic material, they will be arranged randomly. Therefore, net magnetic moment, it will be zero. Therefore, magnetic moment of each atom, randomly arranged atom, it will be cancel each other. Therefore, net magnetic moment, it will be zero. On applying magnetic field, the atomic dipoles align with applied field due to torque acting on it. When you applied an external magnetic field, this atomic dipoles, they will get aligned in the proper direction. Therefore, it will possess some amount of magnetic moment. Hence, paramagnetic substances are weakly attracted by the applied magnetic field. Induced dipole occurs very less. Here in this case, induced dipole, it will be very less. Therefore, paramagnetic substances are weakly attracted by the applied magnetic field. Next one, properties of paramagnetic substances. First one, the magnetization I is positive due to dipole alignment. When you applied an external magnetic field, the atomic dipoles in a paramagnetic material, they will get aligned in the proper direction. Because of this alignment, they will get magnetized. Therefore, magnetization I, it will be positive due to the alignment of dipole moment. Then second point, magnetic susceptibility zeta is small positive. Zeta, it will be greater than 0. For example, zeta value 2.3 into 10 to the power of minus 5 for aluminium. Here you can see magnetization I, it will be directly proportional to zeta. If magnetization is positive, then zeta is positive. Positive means it will be greater than 0. Third point, when a paramagnetic substance is kept in an external magnetic field, the magnetic field inside the paramagnetic substance is slightly greater than the external magnetic field. Here also you can observe, if you applied an external magnetic field, the atomic dipoles in paramagnetic substance, they will get aligned in the proper direction. Because of this alignment, the magnetic field inside a paramagnetic material is slightly greater than the external magnetic field. Fourth one, when a paramagnetic substance is placed inside a magnetic field, the magnetic field lines become slightly more dense in the paramagnetic material. You know, magnetic field inside a paramagnetic material, it will be more compared to the external magnetic field. Because of this reason, the magnetic field inside a paramagnetic material, the magnetic field lines becomes more dense compared to the external magnetic field. Then fifth point, in a non-uniform magnetic field, a paramagnetic substance tend to move from weaker part of the field to the stronger part. In the case of a paramagnetic material, because of the less induced magnetic dipole, if you placed a paramagnetic material in a non-uniform magnetic field, then paramagnetic substance tend to move from weaker part to the field to the stronger part. Next property, sixth one, relative permeability mu r is greater than 1. You know the formula, mu r, it will be 1 plus zeta. In the case of a paramagnetic material, zeta is small positive. Therefore, relative permeability, it will be greater than 1. Seventh property, the behavior of paramagnetic material is temperature dependent. Susceptibility varies inversely with temperature. Susceptibility, it will be inversely proportional to the temperature. SI unit of temperature is Kelvin. Look at the graph here between zeta and T. You will get the graph like this. This it will indicate zeta is inversely proportional to temperature. Then if you remove this proportionality constant, zeta, it will be equal to C by T. This one we will call it as a Curie's law. Let us discuss in detail ferromagnetism. First point, there are atomic dipoles in ferromagnetic material just like paramagnetic material. You can observe atomic dipole in ferromagnetic material because of the presence of an unpaired electron. Then one more important thing here is domain theory. In ferromagnetic materials, the atomic dipoles interact with each other in such a way that they spontaneously align themselves in some direction in small volume called domains. In the case of a ferromagnetic material, the atomic dipoles, they will get arranged in the terms of a domain. This domain size, it will be 10 to the power of minus 12 meter cube. Then number of atoms in each domain, it will be 10 to the power of 20 atoms. Normally you can observe 4 domains here. Then in each domains, the alignment of atomic dipoles, it will takes place. When an external magnetic field is applied, two things it will occur. First one is domain growth, second one is domain orientation. Domain growth means the domain aligned with external field grows in size and other domain reduce in size. Domain orientation means the domain tend to align in the direction of an applied field. Let us see in the next slide. These are the domain. When you applied an external magnetic field, then you can observe two effects here. One is domain growth, another one is domain orientation. Domain growth means one domain, the size of one domain, it will be increased, then the size of the remaining domain, it will be reduced. Next one, domain orientation means if you applied an external magnetic field, then remaining atomic dipoles, they will get aligned in the direction of an external magnetic field. They will get aligned in the same direction of an external magnetic field. Examples of ferromagnetic substances are iron, nickel, cobalt, alloys like alnico, etc. Hence, ferromagnetic substances are strongly attracted by the applied magnetic field. Let us discuss next one, properties of ferromagnetic substances. First one, the magnetization I is large positive due to domain formation. When you applied an external magnetic field for ferromagnetic substance, then you can observe a domain formation. In domain formation, you can observe a change in size of the domain and domain orientation. Because of this, the material, it will get more magnetized. Then magnetization, it will be large positive. Second one, magnetic susceptibility, zeta is very large, because magnetization is directly proportional to zeta. If magnetization is more, then magnetic susceptibility also it will be more, it will be very large. Then in the case of a diamagnetic material, zeta value is -10 per -5. Then in the case of a paramagnetic, plus 2.3 into 10 to the power of -5. But in the case of a ferromagnetic material, the magnetic susceptibility is very large. It will be 10 to the power of 3. Then third point, when a ferromagnetic material is kept in an external magnetic field, the magnetic field inside a ferromagnetic material is greatly enhanced. If you applied an external magnetic field, then the magnetic field inside a ferromagnetic material, it will be more compared to the external magnetic field. Fourth property, when a ferromagnetic substance is placed inside a magnetic field, the magnetic field lines become highly dense in the ferromagnetic material. If you placed a ferromagnetic material in an external magnetic field, because of the strong field inside the ferromagnetic material, you can observe a magnetic field lines, they will become more dense. Fifth one, in non-uniform magnetic field, a ferromagnetic substance tend to move quickly from weaker part of the field to the stronger part. Next one, relative permeability, mu r is much greater than 1. You know the formula, mu r, it will be equal to 1 plus zeta. Zeta is very large, therefore the value of mu r also it will become very large. Then seventh one, the behavior of ferromagnetic material is temperature dependent. Let us discuss in detail in the next page. First point, the ferromagnetic behavior of a substance become temperature dependent. Let us discuss here. In the case of a ferromagnetic material, when temperature increases, then kinetic energy of the atom increases. When the kinetic energy increases, then atoms they will start moving randomly. When they start moving randomly, then alignment of atomic dipole it will get disturbed. If alignment is not proper, then automatically the magnetization also it will get reduced. With the rise of temperature, susceptibility of ferromagnetic material decreases. As the magnetization decreases, magnetization is directly depends upon the susceptibility. Therefore, susceptibility also it will be decreases. At a certain temperature, ferromagnetic pass over to paramagnetic. This transition temperature is called Curie temperature or Curie point. If you increase the temperature, then the atoms they will gain more kinetic energy, then moment of the atom it will be more, then alignment it will get decreased, then magnetization it will get decreased. At that particular point, ferromagnetic material it will be converted into paramagnetic material. That transition temperature we will call it as a Curie temperature or Curie point. For example, Curie temperature for iron is 770 degree centigrade. At a temperature above the Curie point, A ferromagnetic becomes an ordinary paramagnetic whose magnetic susceptibility obeys the Curie-Weiss law. Zeta, it will be inversely proportional to 1 divided by T minus Tc. T is the absolute temperature, Tc is the Curie temperature. When any ferromagnetic material, if it is attained Curie temperature, if you increase the temperature, then ferromagnetic material, it will start behaving as a paramagnetic material at the point of Curie temperature. This one we will call it as a Curie-Weiss law. According to Curie-Weiss law, at temperature above the Curie temperature, the magnetic susceptibility of ferromagnetic material is inversely proportional to T minus Tc. Already I explained magnetic susceptibility is inversely proportional to T minus Tc. Here you have to remember, above the Curie temperature, if you raise the temperature, ferromagnetic material, it will become paramagnetic material. Thanks for listening my class. Send me your valuable feedback.